Okay, so in this packet, I want to start out with problem number 79. How many of you made it up to problem number 79? One of you? Okay, that's promising. So anyway, the reason I want to do number 79 is because it's actually a relatively simple problem if you see how to approach it. The reason I say that is because the relationship is hidden a bit. So here's our part. I didn't draw in all the details, but that's close enough. All that we really care about, even though that hole changes diameter, all of our dimensions are just to the center line of the hole anyway, so that's all that matters. We have a 1 inch here, 2.83 inches here, 2 inches tall, and this is the dimension we are looking for. Does anybody see the relationship here? You do. Okay, what is it?
Stacked over vertical.
Yeah. If we look at it, we have this dimension right here. We'll change colors so I don't end up with issues here. If I move these pieces, I put them together and I realize all it is are similar triangles. That these dimensions here, the larger dimensions, are part of the triangle that's an enlargement of the triangle created by the smaller dimensions. And once I have it pulled out and set up like that, the ratio proportion is simpler to do. It's easier to see. So now, as Jared said, I could either do slant over vertical, so I could do 1 over x here. What would go in the other proportion? 2.83 goes on top because it is the slant, and the 1 is also the slant. 2.0 on bottom. That's one way we could set it up. But remember, we talked about this last week. There's a relationship this way and a relationship this way. And as long as those relationships are maintained, it doesn't matter what direction they go. I could have also have set this up as 1 relates to 2.83 because those are both the slants. Then it would have been x relates to the 2.0 because the x is in the same triangle as the 1. But you'll notice the relationship's still here. Here the 1's related to the x vertically, here it's related to the x horizontally. It's still there. And you'll also notice the calculation is still exactly the same. 1 times 2 divided by 2.83. 1 times 2 divided by 2.83, which is 0.7067. Yes. So that's one of the tougher things about some of these drawings, especially the drawings you guys will work with in the shop, is pulling out the dimensions that have to be similar and turning them into, you can't always pull them out and make triangles like this, but you should still be able to connect which dimensions have to go together. Okay, I'm going to actually then jump up to number 78. Actually, the first number 78. No extra charge for the second one. Here we're looking at alloy ratios. So we're making bronze. It is a 10-to-1 copper to tin ratio. And it's asking, if I have 32 pounds of copper, how much tin would be used? So it's 10-to-1 and the top number is copper. Where's the 32 go? It goes on top because it's copper. And then, of course, it's cross multiply and divide. And Jason was right. It's 3.2 pounds of tin.
See, but I can do that in my...
Oh, because it's a 10-to-1 ratio.
Right, it gets in my head. I didn't have to go through the steps.
Yep. We could also have like a 7-to-2 ratio. Let's say we've got a copper nickel which is a pretty common alloy. Let's say we want to alloy with 63 pounds of copper. Cu, by the way, just for those of you who don't know, is the abbreviation for copper, because Co is cobalt. So anyway, how are we going to set this up to figure out how much nickel we need to combine with 63 pounds of copper?
63 over 1.
63 over X. We don't know what that is yet. And the 63 represents copper, so it's got to be 7 here over 2. So cross multiply and divide, we should end up with 18. Here's a little bit tougher question for you.
No, I don't.
Still using the 7 to 2, how much copper and nickel to create 108 pounds of alloy? If I have to maintain that 7 to 2 ratio of copper to nickel, I need a total of 108 pounds.
All right.
Well, which one of these numbers represents the total? Trick question. Neither one of them does. Neither one, the 7 or the 2, is representing a total here. The 108 represents the total.
Right.
So how do I find a total? Well, if I have 7 parts copper and 2 parts nickel, that would make 9 parts total. So if I want to find the copper is 7 out of the 9 total parts. How much will that be out of 108 pounds? Cross multiply and divide, that should come up with 84. Now I got to go back and do the nickel, which is 2 out of the 9 total parts. Now yes, I realize I could just take 108 minus 84, but I want to do the ratio to figure it out. That way I can add them up later to double check. Is how much out of 108? Cross multiply and divide, I should come up with a 24. This is a very common practice when dealing with ratios, especially when you're dealing with a component ratio like this, where you're taking 2 components that are being put together to make a finished product. If you have a total amount, you have to use the ratio, you have to adjust the ratio. There are all sorts of hidden ratios when you're dealing with things. Just to jump into the medical field, one of the ratios we end up using in the medical field is dilution. It can be used in all sorts of other fields as well. If you have a very concentrated chemical and you need to dilute it to get it down to a certain strength, 1 in 6 dilution and like I said, this might be for lubricants. Some lubricants need to be diluted. A lot of cleaning supplies need to be diluted. If you're doing any sort of acid etching or surface treatments like that, many of those chemicals are diluted. So a 1 in 6 dilution means 1 part of chemical in 6 total parts. So if I want, let's say I need to create 54 quarts of this solution. I need to know how much chemical and then how much water. We're just going to assume we're using water to dilute it. Well, to find the amount of chemical, it's really easy. The ratio of chemical to total is 1 to 6. Do we know either the chemical or the total? Yeah, we want 54 quarts. So that one's ready. The total of 6 we can use. We cross multiply and divide, we end up getting 9 quarts of that chemical. Now again, we could subtract to get the amount of water, but let's look at the proportions, the ratios. The 54 total quarts is still there. The 6 total parts is still there, but how many parts of that are water? 5, good. If 1 out of 6 parts is chemical, the other 5 parts has to be the remaining fluid, in this case the water. Cross multiply, 5 times 54 divided by 6 gives us 45 quarts. The point I'm trying to get across with these last few examples is when you're dealing with ratios and proportions, know what the numbers stand for. Because there's always other ratios that you can create from those. But you can't do that unless you know what the numbers are. Here we're given total parts. Once we know that's the total parts, we can find the other parts just by subtracting. On this previous example with the copper and nickel, we were just given the two ingredients, the two components. And then we were able to use those components to get the total parts. So you're going the other direction. I quite often, when I set up my proportions, will actually label, like you see I put the total here, I will actually label those when I set up that ratio so that I know when I'm setting up the other ratio what it stands for, what needs to go there. By the way, that whole process of a dilution, I'm not going to get into it real heavy here, but let's say you have a chemical, an acid or whatever that you're going to use. That acid is coming at you, it's a 60%. At 60%. And you need to know how to dilute it down. You want to use it at 12%. And let's say you're going to need, what do I want there? Well, let's just say you're going to need 25 cups of it. To do this, first of all, to figure out what dilution is required once you have the percents, let's find the diluted percent over the concentrated percent. In this case, what's the diluted percent? 12%. Concentrated percent? 60%. Notice I dropped the percents because there's one on top, one on bottom. They would just cancel out anyway. I don't want any confusion by having that percent symbol in there, because when you see a percent symbol, people tend to move the decimal point. 12 over 60 is our ratio. Or 0.12 over 0.6 would be our ratio. They're the same, and I'd prefer to work without the decimals in it. Over here now, well, I can, first of all, I'm going to reduce that. Both of those can be divided by 12. It gives me a 1 in 5 dilution. What do those numbers represent? What's the 1 represent? The amount, now that it's been reduced to a dilution, remember the first number in a dilution is always the chemical, or the concentrate, if you want to do the concentrated chemical. And the 5 is, the bottom number is always the total. So it's chemical to total here, 1 to 5. Do I have either of those numbers up here? The amount of chemical? No. Do I have the amount of total? 25 cups. If I cross multiply and divide here, of course I'm going to get 5. What does that 5 represent? 5 cups of, what did the 1 represent? That is the concentrated chemical. So I'm going to use 5 cups of the concentrated chemical. Now, of course, I can do 25 minus 5 to get 20 cups of water. Or, if it's 1 out of 5 parts chemical, 4 out of 5 parts are the dilutant, or the water. Cross multiply and divide will give us 20. Make sense? You look confused, Jason. It's your normal look. Does this make sense, sort of? Like I said, the dilution isn't a huge deal to me. I mean, it is a good application of this. The bigger point is make sure whenever you have a ratio, know what each number stands for, and make sure that you check, is one of those numbers what you're looking for? And is the other number something you have, a piece of information you have? And if not, you look at that ratio and see what you can find. Because in a 1 in 5 dilution, a 1 to 5 dilution, of course, you have the concentrate or the chemical here and the total. That would also give you a 4 to 5 of water to total, ratio of water to total. Or it could give you a 1 to 4. What's that ratio going to represent? Well, the 1 is the chemical concentrate, and the 4 is the water. In some cases, that ratio is handier to have. For every 1 cup of chemical you throw in there, you need 4 cups of water. If you don't have a specific total you're shooting for, you're just mixing up a batch to have on hand. So there are 3 ratios in that single ratio that's given that you can use for whatever calculation you're looking for. Okay, enough of that. I did want to hit a little bit on like problem number 74. Mechanical advantage. You guys talk about mechanical advantage in the shop at all? You guys don't have a formal science class anymore. When you went from the 2-year to the 1-year, your science class got cut. But I am a physics teacher, so I'll sneak a little bit of science in here for you. No extra charge, don't worry. So anyway, mechanical advantage is trading, well, yeah, it's trading weight or force for distance. So like here, let's say I have something rather heavy that I want to lift. The way this is set up, if I push down right here, I'm going to lift that relatively easily. But I may have to push this far, and over here, it's only going to lift up about that far. In reality, the numbers are a little bit blurrier because there's things called friction and other, energy loss to real life things like air resistance and all that wonderful stuff. But in the theoretical world, if you can ignore friction and all that other stuff, the ratio of the force is equal to the ratio of the distances. So let's say that this over here is a 200-pound object. And over here, this distance is 8 feet, and this distance here is only 2 feet. How much force would I have to exert here to lift that up? Well, the ratio of the distances is 8 to 2. The ratio of the force, is this going to be smaller or larger than the 200? Better be smaller, right? So that means the 200 has to go on top. Now, here's the tricky part. The 200 represents the force over here, but the 8 represents the distance over here. They're not linked together like they should be, which tells us, one, that this is an inverse proportion. Remember that word. Bless you. In an inverse proportion, one of the relationships ends up getting flipped because when one value goes up, the other value goes down. When the distance goes up, the force required goes down. We cross multiply and divide here. 2 times 200 divided by 8 gives us 50 pounds. Only 50 pounds of force. Now we said when we're doing inverse proportions like this, remembering to flip over one of the ratios, which is basically what we did here, can be tricky. An easier way to do it is to use a constant product. In this case, the constant product we're getting is work. Work is equal to force times distance moved. The amount of work put into a system, which is the force being applied right here, has to equal the amount of work coming out of the system, which is moving this object over here. So we have a force that's moving 8 feet. That has to equal the 200 pounds moving 2 feet. Look familiar with our pulleys and our gear ratios and stuff like that? So 200 times 2 is 400, and then we have to divide by 8. So we still get 50 pounds. It's just writing it out this way makes more sense to me. And by the way, that ratio of input force or output force to input force, you lifted 200 pounds with only 50 pounds of effort. That is what's called the mechanical advantage, a 4. This magnifies your force by 4. Is there ever any reason to have something with a mechanical advantage less than 1? Let's start out this. Would there ever be a reason to have something with a mechanical advantage of 1? Well, I can think of a couple of reasons. Here, if there's a box here and I'm pushing down here, because this distance and this distance are the same, the mechanical advantage would be 1. Whatever the weight of this object is, I have to use that much force here to lift it. Would there be any advantage to doing that? Well, there might be, because gravity helps me when I'm pushing down, right? Sometimes, even though the mechanical advantage doesn't reduce the amount of force you have to put into it, sometimes changing the direction. Sometimes it's easier to push than it is to pull, or easier to push down than it is to lift up, changing the direction of the force. Other things, mechanical advantage less than 1. Sometimes you want things to move faster. Well, you make them move faster, you have to put in more force to make it happen. Things like that. Okay, enough of that. Let's finish off this packet. We're going to flip to the very back page of the packet. The last concept you guys need to know before we finish off Unit 1, and you are totally prepared for your test tomorrow. So let's say we have a ratio where we're adding chemicals. And actually not a ratio, this is actually a rate because we have the units in it. Let's say you're going to add 12 ounces of chemical, oops, I don't know what happened there, to 5 gallons of liquid. We want to know then how many tablespoons would that be in 2 quarts. So that's 12 fluid ounces into 5 gallons. How many tablespoons into 2 quarts? Can we do this ratio, this proportion right now? Again, it's not ratios, it's rates. Careful. Yeah. It's okay to have fluid ounces compared to gallons here because it's a rate. A rate has different units. Problem is, in a proportion, whatever the units are here, we have to have the same units there. Same here and here. Those two have to be the same. So what I would really like to do is convert. Usually it's easiest to take whatever it is I'm looking for, in this case the tablespoons here, and convert to that unit. So anybody know how many tablespoons are in a fluid ounce? 1 fluid ounce is 2 tablespoons. So, of course, 12 fluid ounces would be either 6 or 24. Which one is it? Well, is a tablespoon bigger or smaller than a fluid ounce? It's smaller. So if the unit gets smaller, the number has to get bigger. Remember our conversion from last semester? 12 fluid ounces. We put it over 1. We're getting rid of fluid ounces. That has to go on bottom. Going to tablespoons. 2 tablespoons is 1 fluid ounce. Fluid ounces cross cancel. This is telling you it's multiplied. 12 times 2. Look familiar? It's been a couple months. That's one of those, especially in machining. Keep that one handy because you are going to use it more than once or twice in your career. So now down here, I gotta be careful. I didn't want the 24 tablespoons there. I wanted to put it here. So now down here, I either need to change this into quarts or quarts into gallons, one of the two. Probably easier to change gallons into quarts. How many quarts in a gallon? 4. So 5 gallons over 1. Gallons are going on bottom, quarts on top. So what numbers go here? 1 gallon is 4 quarts. Good. Gallons cancel. 5 times 4 is 20 quarts. So this is now 20 quarts instead of 5 gallons. So these numbers are gone. I converted them to 24 tablespoons over 20 quarts. Cross multiply. 24 times 2 divided by 20 is 2.4 tablespoons. What do you think? Loads of fun? So how about this one? Let's say something comes in at 80 PSF. I want it converted into OSI. Anybody know what OSI? What's PSF stand for? Pounds per square foot. What's OSI stand for? Ounces per square inch. Good. So this is 80 pounds per 1 foot squared. And I want to know how many ounces that will be for 1 inch. Where'd this 1 come from in the inches squared? Well, the same place the 1 in the feet squared did. When I'm per square foot or per square inch, it's applying per 1 square inch or per 1 square foot. So now I need to do some conversions. I can change 80 pounds into ounces. How do I do that? You got it. 1 pound, 16 ounces, which is going to give us 1,280, right? Sure. You guys are agreeable. Then what do I need to do? Square feet, 1 square foot. How many square inches are in 1 square foot? 144. Good. Somebody said 1728. Remember, 1728 is square inches or cubic inches in a cubic foot. So 144 square inches. Now we can cross multiply and divide. 1280 times 1 divided by 144 gives us 8.89 ounces per square inch. Questions? Okay, well, you should now be able to complete this packet. So it'd be problems 1 through 92, with the exception, of course, of numbers 44 and 45. 45, remember, is worth 20 points if you can get me the correct answer. Considering the test you're going to take tomorrow is only a 100-point test, that's a pretty healthy bonus question. I'll give you till the end of spring break to have an answer to that question. How's that sound? So you got 4 weeks, 4.5 weeks yet?